Hi guys, we will solve these questions. This is the worksheet 8, right? So I will solve all of the questions except the last one. We will solve them online. So let's start with the first one. It's about fundamental theorem of calculus. So here you have the recall. Okay, so we're given a function g of x. We will find its derivative g prime of x. And it's given by an integral of a function, which is 2 plus sinus t, right? Now we will find g prime in two ways. First, we will apply the first part of this theorem and then the second one. So what's the assumption in the first one? We have a function inside f, right? So it should be a continuous function of some interval. You see, we have 2 plus sinus t, so it's always continuous. Sinus t is continuous, 2 is continuous, then the sum of them is again continuous. So we have the assumption, okay, this function is continuous no matter what the interval is. So we can apply the theorem. Now, what does it say? We have this integral from some constant, here we have 0, and to x, as in here, we have x. Then we can directly write this equality. So g prime of x is the derivative of this integral, and apply in the first part as we have the assumption. Apply in the first part we get 2 plus sinus x, right? We just write t equals to x there. Okay. And the second part, what do we have? We need to find an antiderivative of this function f. So here we have the antiderivative. This is the antiderivative of this function, okay? Here we consider as the constant is 0. I mean, by constant, I mean. So if this is the antiderivative of, cosinus t plus some constant, let's call c, right? This is also an antiderivative of this function, f of t, right? If you take the, what does that mean? If it gives this equality, then we call this uppercase f antiderivative. So if you take the derivative of this function, you will get the same thing. You will get this lowercase f of t. So this is also an antiderivative, but here we will consider as c equals to 0, because when we evaluate it, eventually that c is, will be cancelled out. So we will have the same thing. Thus, it doesn't matter if what constant we have there. Okay, so we ignore it. We take it as 0. So this is the antiderivative of this lowercase f. Thus, we apply the theorem as you see here. So we plug x, then 0 instead of t there. So when t equals to x, we get this. When t equals to 0, we get this. Cosine 0 is equal to 1. So we have this result. Now, what's the derivative of g then? This gives only g of x, right? The derivative of g is then the derivative of this with respect to x. So we get 2 plus sinus x, okay? As you see the same result with the previous one, of course. So we're done with this question. So we will apply this theorem again to find the derivatives of these functions. Okay, the second question. Okay, I will solve only a, c, and f. Now you see we have a function g. It's given by this integral. The function inside is continuous, and we have a constant there. We have x above, so we can directly apply the theorem, the first part of this theorem. What's g prime of x then? Just plug t equals to x here and get this result. You see we have x below, and as constant above, we cannot apply directly the theorem. Cosinus square root of t is always continuous, but we need to make some change here. So we will, if we multiply it by -1, we will get this integral as we want to want to apply the theorem. So now we can take the derivative. G prime of x is then equal to this, right? Now, what about f? So we have here sinus x and there 1. Even if we multiply it by -1, we will have above sinus x, not x only. So we need to make some substitution there. Let's call u, the sinus x u. Okay, we make the substitution and take the differentiation. And then we get du is equal to cosine x dx. Now we had before this equality, right? We want to find y prime. Y prime, by y prime, we mean dy over dx. So dy over dx is equal to dy over du times du over dx, right? So we need to find these ones, all right? Now, what's du over dx? It's here. If you multiply both sides by d over dx, okay? So you will get du over dx is equal to cosine x, as in here, all right? Then the only thing we need to do is to find dy over du, okay? And as sinus x is equal to u, we have this integral now, okay? Now it's the same when we had x there. It's the same to find d over dx, okay? Only we have here the variable u. Then, as we did here in the previous part, we multiply it by -1, so we get some variable above and a constant below, right? Now, what's the derivative of this integral with respect to u? It's just plug t equals to u, right? The function inside is continuous, so we can directly plug t equals to u. So we have this. And we had before this multiple cosine x. So this is d over du, this first part. And this is du over dx. Okay, now we need to find dy over dx. So all terms should be in terms of x or constant, right? So instead of u, we need to write some function in terms of x, which was here, u is equal to sinus x. So we just plug u equals to sinus x and get this function, okay? And the third question, here we have. So this part is easy, right? We have, let's write it together. So the derivative, the integral of this function pi is pi x from -5 to 5. You just plug 5 there first, x equals to pi, x equals to 5 will give us 5x, 5 pi. And if we plug -5, we will get -5 pi. So we had before minus here, as we need to subtract them. We have 5 pi again, so we get 10 pi, right? These are pretty simple. Let's just solve them and pass to the next question. So how do you find it? We have x to the -2 over 3 plus 1 over the same power here, right? So we have, if you add them, you will get 1 over 3 from 1 to 8, okay? So let's write here again, 1 over 3. So we have in the parentheses of, so this 1 over 3 will be 3 there. So we evaluate this one, right? From 1 to 8. So if you plug 8 there, as we have 1 over 3, we will get 2. And if you plug 1, you will get 1. So we have 3, right? These were pretty simple. So what about this? Here we have in the denominator, we have x to the 1 over 2, right? So if we multiply these terms by this one, what do we get? Here we have x over, so this is from 1 to 9, x over x to the 1 over 2 minus 1 over x to the 1 over 2 dx, right? So this can be written like this, and this can be written like this. So here we have x to the 1 over 2, and here we have x to the -1 over 2. Now we can take integrals separately, right? So this one's integral is here. We just add 1 here to the power and we divide it by its power. The same here again. So we plug first 9, then 1 and subtract them, right? As you see here, the rest is easy. Now, what about this? We have, so here, this can be written like this. From 1 to 3, e to the z to the 1 over 2 dz, right? So z times 1 over 2 will give us z over 2, right? Now, what's the integral of this? We write the function e to the sum, the integral of e to the sum function. Here I assume that u is a function of x, okay? So the integral of that is e to the u over u prime of x, okay? So here we have z, right? So we write the function directly, then we take the derivative of that with respect to z, okay? So it's 1 over 2, thus we get 2 times e to the z over 2. We plug z equals to 3 first, then z equals to 1. It gives us this, okay? This 1 over 2 can be written as 2 here. So we have this. All right, what about this? This 4 can be written outside of the integral. It doesn't depend on x, so we have 1 here. And the integral of 1 over x is ln of x, the logarithm function. And we evaluate it from 1 to 4. So we just plug first x equals to 4, then x equals to 1. All right, so we get this. Ln 1 is equal to 0. So we have 4 ln 4. Right? And if you want, this is equal to 2 squared, right? So you can write this 2 as a multiple here. So we get this. You don't have to do that, but you can if you want. All right, first remark that the derivative of secant theta is equal to secant theta tangent theta, right? So this function secant theta is an antiderivative for this function, right? So its integral will be equal to secant theta. And we need to evaluate it from 0 to pi over 4. So if you plug first, secant theta is equal to, by definition, this is equal to 1 over cosine theta, right? So we first plug theta equals to pi over 4, and we get this. And then theta equals to 0. Cosine 0 is equal to 1, and cosinus pi over 4 is equal to square root of 2 over 2. So we have this. And finally, the last part of this question 3. So we have a function f, which is defined piecewise again, okay? So we need to first separate this function into 2, separate this integral into 2. So between 0 and pi over 2, so we separated with respect to these endpoints, all right? So between 0 and pi over 2, the function is defined by sinus x, and between here on this interval, it's defined by cosinus x. And this one's integral is minus cosinus x, right? When you take the derivative, you will get sinus x. So this is antiderivative of this function. And the the integral of cosinus x is sinus x, right? From 0 to pi over 2, from pi over 2 to pi. So when you plug here, when you plug pi over 2, you will get 0. So minus cosinus pi over 2 minus cosinus 0, you have plus sinus pi minus sinus pi over 2, right? So cosinus pi over 2 is 0. This is 0. This is equal to 1. So you have minus times minus 1, you will have 1 there. Sinus pi is equal to 0 again. sinus pi over 2 is equal to 1. This is equal to 1, so we have minus 1 there, so we get 0. All right, I leave this question to you, okay? I leave that as an exercise for you. And the 6 too, right? We will solve 5 and 7. If you have any question, we can start with them on online class. Now we will find the derivative of this function g of x, okay? Now we have this, let's look at here. We have tangent x and x squared, okay? We cannot directly apply the theorem, the fundamental theorem, right? So we need to play with these first, these boundaries. So we can write it as a sum of these two integrals. So we separate this integral into two. So from tangent x to some constant a, and from some constant, from this constant a to x squared. Okay, we can separate it. Now we multiply it by -1. Why do we do that? Because remember, we need to have a constant below and a variable x or u, right? A single variable above, right? So we multiply it by -1. Thus we have this integral plus this one. This was already here constant and then above x squared, so we don't do anything there. Now for to find the g prime will be equal to the derivative of these two integrals, right? So first we need to change this one into a variable u. So if we call u equals to tangent x and v equals to x squared, then what do we have there? What do we have there? We have g prime on the left, so it's the derivative of g with respect to x, right? And so it can be written like this. Let's write here dg over dx is equal to, first recall that this is equal to now u and this is equal to v, right? So dg over du over dx plus dg over dv over dx, right? As you see here, we have du over dx, dv over dx, and dg over dv, and dg over du, right? All right. Now, what do we have here? What's the derivative of this? If we apply the fundamental theorem, we just need to write t equals to u there, as we have this variable u there, okay? This is, the function is continuous, right? A is some constant, so this function is continuous. As t squared is always positive, the denominator is never 0, so the function is continuous. So what do we have? We plug t equals to u there and times du over dx plus, again, the function is continuous, so we just directly plug v equals to t, or t equals to v, so we get this dv over dx. And du over dx, here we have the equality, you know that the derivative of tangent x with respect to x is equal to secant squared x, and dv over dx is 2x, right? So we have this now. And remember, we need to find dg over dx, so all terms should be in terms of x. So we just plug u equals to tangent x and v equals to x squared and get these, right? Now we have this. So f of x is given by this integral, g of y is given by this. We need to find g double prime of pi over 6. So we're given this function, right? So what's the first derivative? Let's look at, let's find out first what do we need? So what we need, right? So g prime of y is equal to, here we have some constant, we have variable y, so applying the theorem, the fundamental theorem, we get f of y, right? So just plug x equals to y, we will get f of y there. Now, if we take the derivative again, we will have g double prime equals to f prime. So we need to find f prime to get g double prime of pi over 6. Let's find first this one. So here we have 0, so some constant, it's okay. And here sine x, so we need to play with that. So if we plug again u equals to sine x, we make the substitution and take the differentiation, we get du equals to cosine x dx. Okay, just taking the derivatives gives that. What do we get now? F prime of x equals to, as we did before, it's d over du. So this function's derivative with respect to u, then du over dx. You see du over dx is equal to cosine x, right? And here we have some constant, we have a variable, simple variable. So we just plug t equals to u and get this. Du over dx is cosine x, so we get this. As I said before, all terms should be in terms of x, so we just plug u equals to, again, sine x. So we have this. This is f prime of x, okay? G double prime was equal to f prime of y, so we just plug x equals to y there, okay, which is this. So g double prime is equal to this function. What do? We just plug y equals to pi over 6 to get this value, right? So f prime of pi over 6 is equal to that, and you know the rest. Okay, you know the values of these functions, okay? The rest is easy. Now, all right, let's first solve this question, okay? So now first you can stop the video and read the question, okay? So the first question, first part of this question asks asks us the representation of this integral, okay? Why this function, this integral represents the loss in value of the machine over the period of time t, okay? So if we denote by, let me write here. So if this function f of t, so like this function represents the loss of the machine over t, over the period of time t, okay, then what do we get? Then, as this is the rate, okay, then what do we get? The derivative of this function, this uppercase of f, uppercase f of t, the derivative of this function will be given us the rate, right? So it will give us f of t, right? Now, what do we have on the other hand? We had before this, from 0 to t, f of s ds, this one, right? So it is then equal to, as this is now the antiderivative of this lowercase f, right? This is the antiderivative of this lowercase f. So applying the theorem, fundamental theorem, gives us this one from 0 to t, right? Just plug s equals to t and s equals to 0. We have f of t minus f of 0. F of 0 is equal to 0, so we get f of t, right? So that's why this function, this integral, represents the loss in value over the period of time t, right? So we're done with the first one. What about this? Now, we can rewrite this equality as in this form. Let's write it here. So I will write it here. So C of t is equal to this one, 1 over t times this function. And we've seen before in the previous question, in the previous part of this question, that this is equal to f of t, right? So it can be written like this, a plus f of t. And they both represent the loss of the value, right? So that's why it represents this C represents the amount of money loss, okay, between the repairs of the machine, okay, as it can be written, it can be seen as 1 over t times a plus f of t, and f of t was representing the loss. A is already here, it's the cost, it's again representing the loss. So C is this function represents the amount of money loss, okay? And that's why, of course, the company wants to minimize this C, okay? And what about the last part? So we have this function C of t, okay? We want to minimize it. Recall that in the previous classes, we've done this for some functions, which one variable function. We take the derivative and equalize it to 0 to apply the derivative, the first derivative test. Okay, so we need to find the derivative of this function and equalize it to 0 to minimize that. So what's the derivative of this function? We need to equalize it to 0. So we have a product there, right? Let's find it on the whiteboard. Okay, I don't have enough space there. Right, so oops. Now the part C of t is given by 1 over t, a plus integral from 0 to t f of s ds, right? So we will find the derivative of this function and equalize it to 0. So 0 is equal to c prime of t. We have a product there, so the first we will apply the product rule to take the derivative. So the first one's derivative is minus 1 over t squared times the second one plus first one times the second one's derivative. This is a constant. This uppercase A is a constant, so we only take this one's derivative. And what's this derivative? Just apply the the fundamental term, as we have constant here 0 and a variable there t. So the derivative of this function is f of t by the fundamental theorem. As we have this equality, 0 is equal to that. So let's first rewrite it as in the parentheses of minus 1 over t, we get 1 over t times this integral again, ds, minus, as we have minus there, what do we get? Minus f of t, right? So this product is equal to 0. 1 over t is never 0, so then this one, this parenthesis, should be equal to 0. What does it give then? F of t is equal to 1 over t times a plus the integral of this ds. And you see this is equal to c of t, right? This is equal to c of t. Then if we call that value instead of t, so it happens at some root t, right? So this equality is valid for some value of t. If we call it t, the capital T, then that t, the one which is the root of this equality, that t should satisfy this equality f of t, right? We don't directly find that t, right? Just call it the uppercase t, which is the root of this equality. This is equal to 0, right? So t satisfies this equality. If it satisfies this equality, then it satisfies, as we have implication there, it satisfies this f of t is equal to c of t. Then if we plug t, we will have this equality, right? So we're done with the question. Right. Now this question 9. Here we have. So we have a function f. Okay. We will find that function. Sorry, we will find that function f and the value of a. Okay, so that we have this equality. So we need to find that function f which satisfies this equality. Now what do we have here? We can rewrite this equality as in this form, right? We just subtract 6 of from both sides. We get this, okay? Now taking derivative will give us this equality. So we can take this this integral's derivative using the fundamental theorem if this function inside is continuous, right? So accept for a second that this function is continuous, f of t over t squared is continuous. Then what do we get there? The derivative of this will give us this function. And the derivative of that, as we have some constant a and x here, the derivative of that is just when we plug t equals to x, right? F of x over x squared is then equal to that function. So f of x is equal to this, right? So recall that we can take this derivative using the theorem. We can take this derivative like that if f of t over t squared is a continuous function. You see a is some constant here. If a is, for example, -1, then we take this function's derivative on an interval which contains 0. So it means t can take the value 0. But if can take that value, then the function will not be continuous as the denominator can be 0, right? So it means a cannot be something negative. A cannot be equal to 0 either, right? Because it will give us again something undefined there in the denominator. So if a is greater than 0, this function will be continuous, and it implies that we can apply the theorem, right? So if a is greater than 0, then this f, the function f is this function, okay? And we're done, and it can satisfy this equality, right? So a is greater than 0 and f of x is this function, okay? All right, now this question 10. So we have this part C. Okay, we will solve that integral by substituting this equality. So if u is equal to 1 over x, then du is equal to minus 1 over x squared, right? Now what do we have? We had before this function. So instead of 1 over x, we write u, right? So here we have in the numerator we have second squared u, right, in the numerator, and du is equal to minus 1 over x squared dx, right? Here we have dx over x squared, then it gives minus du, right? So we have this function then, right? Okay, then what do we have? All right, so we had square root of that, second square, and the integral of that, you know that the derivative of tangent is second squared. So what do we get? This is the antiderivative of that function. So the integral of this is equal to minus tangent u plus some constant, as it's indefinite, right? We don't have boundaries. Then we have this minus tangent u plus c, okay? But we need to find it in terms of x. We need to find the result. The result should be in terms of x. So instead of u, we just plug 1 over x and get this one, okay? All right, and this is also, this question also contains the indefinite integral, okay? So let's start with the first part. We just plug u equals to x cube, okay? In general, we start to substitute with the function inside, okay? So I recommend that for you to try first the function inside for substitution. So if we say u equals to x cubed, then du is equal to 3x squared dx, right? So what do we have? We had before this integral, right? You see x squared dx, here we have x squared dx. Cosinus x cubed is cosinus u, as u is equal to x cubed. And we have x squared dx, which is equal to, if we multiply by 3, we have du over 3, right? So we have this function now inside, cosinus u over 3. With respect to u, we can take the integral. It gives sinus u over 3 plus some constant. And as I said before, we need to write the result in terms of x. So just instead of u, write x cubed. So we have this, right? And for this one, we just plug x equals to 1 minus u squared. So if you take the derivative of both sides, you will get dx. The differentiation will give us dx is equal to, this one's derivative with respect to u is minus 2u du, right? So what do we have? You see here, we have u du, okay, u du. So instead of that, we will write minus dx over 2, and this was, well, equal to x, so we have square root of x there, okay? Now we can write this 1 over 2, minus 1 over 2 outside of the integral. It doesn't depend on x. We have here inside x to the 1 over 2, and you know how to find the integral of that. Just add to power 1 and divide it by its power, so we get this, okay? And here you see I made a mistake there. Instead of x, we need to find this result in terms of u. So we had before 1 minus u squared as x. So what do we have? U squared, square root of this over, this is parentheses, over 3 plus some constant. Okay, this is the result. For this part, we have cosinus to the 4 theta sinus theta d theta. So if we say u equals to cosinus theta, then differentiation gives us du is equal to minus sinus theta d theta, right? So you see here we have minus du, right? As we have minus there, it's equal to minus du, right? So what do we get? We had before this integral, this is minus du, right? And cosinus to the 4 theta is equal to u to the 4. So we have minus u to the 4 du, and you know the rest, right? You just add 1 and divide it by its power. Here you need to make back substitution to get the result in terms of theta. Right? And what about this one? We will first substitute this one, u equals to 1 plus x to the 3 over 2, right? Now differentiate that, du is equal to, so write the derivative of this with respect to x, so it gives this one, okay? So basically we have this, du is equal to this one, right? Now, so this is equal to u, right? We make that substitution. So we have sinus u, and the square root of x times dx, square root of x times dx is equal to 2 du over 3, right? 2 du over 3, right? So we have this now. And you see the integral of sinus is equal to minus cosinus u. It should be 2 over 3, okay? So we have minus 2 over 3 cosinus u plus c. And instead of u, we need to have some function in terms of x. So we just make this back substitution and get this result. Okay. Now for that, we substitute this one, u equals to ax plus b, and differentiate it and get a dx is equal to du, right? So a is not 0, so we have this equality, right? Now, instead of this one, this denominator, ax plus b, we have u, right? And you see dx is equal to du over a, right? So instead of dx, we write du over a. So we have this integral. Now you see we take the integral with respect to u, so we have 1 over u there, right? If we write this a outside, we have 1 over a times this integral. So the integral of 1 over u is equal to ln of u, right? Plus some constant. And u is equal to this, ax plus b, so we get this. Now, for this part, we have arctangent t over 1 plus t squared dt, right? So as you can guess, we substitute u equals to arctangent t, and the differentiation gives us du is equal to, you know the derivative of that, it's 1 over 1 plus t squared dt, right? So what do we get? We have dt over 1 plus t squared, it's du, right? And this is equal to u, so we have u du, and its integral is u squared over 2 plus some constant, and now back substitution gives that. All right, what about this? We have sinus x over 1 plus cosinus squared x. So if you plug u equals to, for example, you cannot plug u equals to sinus x, right? So it will give you du is equal to the derivative of this function with respect to x is cosinus x dx. So you don't have such term here. It won't be useful. So if you say u equals to cosinus x, then you will get du is equal to minus sinus x dx. As you see, you have sinus x dx there, so it will work. So instead of sinus x dx, it's minus du over this function, 1 plus cosinus squared. Cosinus is u, so we have 1 plus u squared. And you know, the antiderivative of 1 over 1 plus u squared is arctangent u. We had minus there before, so we have minus arctangent u plus c, right? And u is equal to cosine x, so we're done. Right, now we have this question 12. All right, now we have this function 3t minus 1 to the 5, right? Just plug u equals to 3t minus 1 and differentiate it and get du equals to 3 dt, okay? Then what do we have here? Just instead of 3t minus 1, we write u, so we have u to the 5. And dt is equal to, this gives, dt is equal to du over 3. So we have du over 3 there. Okay, inside we're done with that. What about the boundaries? We had, these are given for t, right? So this is t equals to 0 and t equals to 1. So when t equals to 0, we get minus 1, right? This is minus 1. So when t equals to 0, u equals to minus 1, as this integral is written with respect to u, we need to change the boundaries with respect to u. And when t equals to 1, we have 2, right? U equals to 2, just plug t equals to 1 there, u equals to 2. So we have this integral now. Now what do we have? Write this 1 over 3 outside of the integral. We have this, and the integral of this is u to the 5, right? Its integral is u to the 6 over 6 from minus 1 to 2. Just plug first 2, then 1, minus 1, sorry. You will have this one, and you get the results. No back substitution here, right? We have definite integrals. We just already plug these variables and subtract them and get the value, get the result directly. All right. Now we have this this integral. We first substitute u equals to cosecant pi t, and then du is equal to this one, right? You need to know how to take the derivative of this function. Okay, so we did that before, though. We need to know them. So we have this equality then, right? Now it gives then, so what do we have? We have cosine, we have u equals to cosecant pi theta. So this is u. And oh, sorry. We have this one, cosecant pi t cotangent pi t dt is equal to du over, here we have du over pi, right? This is equal to du over pi then. From this equality, we get this. So we had before this whole thing, so it's equal to minus du over pi, right? So we have this this one inside of the integral. What about the boundaries? When these are given for t, so when t is equal to 1 over 6, we have cosecant pi over 6. And, you know, this is equal to 1 over sinus, so you just plug that. 1 over sinus pi over 1 over sinus pi t. So you just plug t equals to 1 over 6. So sinus pi over 6 you have there. 1 over sinus pi over 6 gives you 2, all right, for you. And when you have t equals to 1 over 2, you will have 1 over sinus pi over 2, and sinus pi over 2 is equal to 1. You will get 1, right? So we have this integral then, 1 over minus 1 over pi. The integral of this this function is equal to u. So we had before this multiple minus 1 over pi. So we have this function from 2 to 1, right? You just plug first u equals to 1, then u equals to 2, and then subtract them. So you will have this. Now we have u equals to sinus x. All right, so du is then equal to cosinus x dx. Right, differentiation gives us this. Du is equal to cosinus x dx. Right. Now what do we have? We have before this integral, right? It's given here. So sinus x is equal to u, right? So we have, what do we have there? This is then sinus. This is sinus u then. And you see cosinus x dx is equal to u, du, right? Dx, cosinus x dx is equal to du. So we have sinus u times du there, okay? And when x equals to 0, sinus 0 is 0, so we have 0. When x equals to pi over 2, sinus pi over 2 is 1, so we have 1 there. Then the integral of sinus is minus cosinus, right? From 0 to 1, just evaluate it and get that. All right, this is the part G, okay? And then we will solve this question 13 and we will stop. All right, here we have this function inside 2 pi t over uppercase T minus alpha, right? So we just plug u equals to that, then du is equal to, with respect, we take the derivative with respect to t, right here. So this 2 pi over t is a multiple of this lowercase t, so it's the derivative. Alpha is some constant, so its derivative is 0, times dt we have. Now we have here, this is equal to u, then we have sinus u. What's dt? From that, you will have t times du over 2 pi as dt. So instead of dt, instead of this, we write that. Okay, we get this. What about the boundaries? This is equal to t, right? So when t is equal to 0, we get minus alpha. When t is equal to this capital T over 2, right? Just write t over 2, so you will simplify them. You will get pi minus alpha. Sorry. So above we have pi minus alpha. Now what's the derivative? What's the integral of this function? It's minus cosinus, right? This one's integral is minus cosinus u. This is always a multiple there, so we don't care about it. So we have this function then, from minus alpha to pi minus alpha, all right? So we just first plug u equals to pi minus alpha, and then u equals to minus alpha, all right? Cosinus is an even function, so cosinus minus alpha is equal to cosinus alpha, right? And you know this is equal to cosine minus cosinus alpha, right? You have pi minus something, right? So you will have, this will be equal to cosine minus cosinus alpha. So what do we have there? Minus, this one is equal to minus 2 cosinus alpha, right? We can simplify these two, and we had before this here minus, so we'll have t over pi cosinus alpha, right? And this is the last question. This one is this one, 14. So here we have a function f which is continuous, and we're given this integral from 0 to 4. We have this one, this integral. We need to find that. So of course we will try to use this. So you see f is a continuous function, and we have this. Now if we plug here u equals to, we have 2x, right? If we plug u equals to 2x, then we get du is equal to 2 dx, right? So we can rewrite this given integral as in this form, as in terms of u. So we have f of u This is equal to f of u, and dx is equal to du over 2. So here we have. What about the boundaries? When here x equals to 0 and x equals to 2. When x equals to 0, we get 0. When x equals to 2, we get 4. So we have this function. It can be written like this. 1 over 2 is outside of the integral. Okay, as we know this equality now, what do we get? 1 over 2 times 10, which gives 5. So we're done. This was the integral we were trying to find, right? So it's 5. Sorry. So we're done with these questions. I will solve these 2 questions on the online class next week. Right? Please watch all of the video. I should have said that in the beginning of the video, but anyways. All right, sorry, see you.